fertility?
Yeah. Well, we have cat. We have SAC as well.
What else are we supposed to have on here before this? Was it just this?
For this one, I think this is the first time that we have, you just record your observations, but you have the HC2H3O2 that is with the calcium carbonate. That's what you find in, that's mainly what the eggshells are made out of. And then you make, this is a double displacement reaction, outer and inner. H and CO3, that will make H2CO3.
Would that be H2?
Yes, that will immediately go into H2O plus CO2, which is the bubbles that you saw. And that's a liquid and that's a gas. And the other one is the calcium acetate, so it's CaC2H3O2. And that will be a solution. You shouldn't see a salt forming. You should just see CaC2H3O2. Yes.
What were like the foam that was like?
The foam was the carbon dioxide being made with little bits of the salt, the calcium acetate, because the
It like
calcium.
stayed there. It didn't like evaporate.
No, what is inside the pockets is the calcium. I mean the carbon dioxide, but it's having some of this calcium acetate in it. That is still some of the salt is actually in there. So, what type of reaction is it? Double displacement. How do you draw a particle diagram? For particle diagrams, I like to, instead of writing vinegar, well, you have the vinegar in here, but for this, I'm gonna replace it with HAC, which is acetic acid, same thing. But writing this every time will make the particle diagram a mess. So this will be calcium acetate, and that way, and that's gonna actually dissociate because you have the acetate, NaAA into +2 and minus. Ooh, calcium acetate. That's a 2 back there that we didn't put in the other class. Okay, so you're gonna have, you're gonna have 2 of these ones. Ca2 plus, well, it's not balanced, but
Do we have to balance it?
ideally, right. Ideally, you should balance it and you have the right amounts. But if you just have calcium acetate, you'll have that. So, the other part.
Just rewrite the equations.
What I did is I'm trying to think about how am I gonna do the particle diagram. So I know the vinegar will be all together, and it's gonna be mainly HAC. I just didn't wanna have to write the whole thing. So I put HAC. That will be easier. It's mostly HAC.
But for the equation, what did you just change?
So I'll show you as soon as I get it. Let me see. So you're gonna have one that is gonna dissociate into H plus AC minus. That's how you draw that one. Calcium carbonate is what? It's a solid. It's the shell. It's an ionic salt, right? This ionic salt will be drawn like we draw any other ionic salt. We just draw them always the same way. It's not 100% accurate, but it tells me that you know that it's a solid, that it's an ionic salt, that is bound, that has an ionic bond that bonds it. Now it's a covalent bond that bonds these ones. The negative side of the anion is all bonded covalently. But just doing that tells me that you know that. Now, this one is all in the same bucket. You have a water line. You have the carbon dioxide. You can just do CO2, or you can draw it better if you want. You have the water. You don't have to draw the water. Then you have the calcium acetate, which you didn't see salt coming out. So in some areas, you may see a little bit of pieces of calcium acetate together where there was not enough water, but especially towards the outside. But you should see that the calcium 2 plus is gonna be little surrounded by oxygen. I mean, the oxygen in the water. making those ion dipole bonds, and then the acetate
Is it bigger or smaller?
bigger. The anions could be the same size, never smaller. Usually bigger. And you need to at least draw one with the hydrated gel just to realize that these are both. Why does it dissolve 100% that we know? Because it actually falls within our rules. The acetate will make it a part of the NaA and it will dissolve. Now the reason I changed this to H2O and CO2 is because that's what you literally see. And I changed this into the calcium and the two AC minuses, because that's what you draw if you were drawing your complete ionic equation.
What type of reaction is it?
Double displacement. You have the H and that, and the Ca and that. And they are going to make a liquid and a gas, so definitely happens. If you make a solid, a liquid, or a gas, that means it will happen. It doesn't happen when everything stays, well, you have a solid, so it's definitely a double displacement reaction.
Do we have to write another chemical equation, like the eggshell in the water, the other places?
The eggshell in the water, the calcium carbonate is not soluble, right? The only reason it became soluble is because you added an acid to it. So no, eggshell in the water will just be this in water, but nothing will happen. If you wanted to draw that, that's what it is. It's the eggshell in water. It will not dissolve or anything. With time, I'm sure everything is somewhat slightly soluble, but no. No, that's it.
Can I go to the bathroom?
Yes. Now, the particle osmosis, you can answer these questions yourselves, but we have this that we hopefully understand very well. I added this because I found this sketch and I just want you to see it. We'll talk about it in more detail with Ms. Purnell when you take AP Bio. But we have been talking about hypertonic and hypotonic. We understand how that works. We know that if we have a semi-permeable membrane and we have a side that is full of stuff, doesn't matter what it is, that will be hypertonic. Stuff that is dissolved, right? And this side is gonna have just water, or it's gonna be way more dilute. Concentrations are going to start, this side is gonna start going in that direction. Some of it will go back, but most of it is going to go until it dilutes it. So you're gonna have more going into that direction than whatever comes back. There is always a dynamic equilibrium, but there's gonna be more. Once it dilutes it, it's going to have the same amount going back and forth, and you're gonna keep the concentrations constant once it dilutes it to a point where you are saturated, where no more you dilute it as far as the concentrations reach this equilibrium. And this is the osmotic pressure that keeps the reaction from continuing. If I wanted to stop this, if I didn't want osmosis to happen, I could add pressure here and it will not allow any water to go in there. But naturally it will reach this amount of osmotic pressure and then the reaction will stop. That's just for you to see and to help you understand a little bit more about osmosis. I don't think I asked a question, no I didn't. So that's if you so you didn't have to do anything else. I just wanted to add it so that you understand that. Now we have the last lab. No, it's not the last lab. We have the distillation and so is everybody done? No, not everybody's done with the egg one. So we have one that is called distillation first. This one again is really, really simple. You can do it in about half an hour or less if if you want to. As long as you at least set it up, anything that you physically do will help you remember things. So in distillation, we are going to separate substances not by affinities, but we're going to separate based on boiling points, right? Oh shit, I wasn't going to tell you that. But if we have water, just plain water, and we've had all sorts of answers on this in the class. So we'll see. We have plain water.
Do we need to draw?
If I were you, I would, just so that I remember how this works, right?
Lab notebook or is it?
I was doing it in the lab notebook because that's what you're turning in. But if you have plain water, that's H2O, and you have water, you have a solution of ethanol, literally any alcoholic drink. So you are gonna have still water, it's mostly water. But then you're also gonna have the ethanol, which is gonna be the C2H5OH. So you're gonna have a few of those. With your OH.
Is there a water line on there?
Yes, we have to draw a water line. Then, what is the intrabond that will happen between all this water? What keeps the waters together and makes it so that it doesn't really boil away that easily? Hydrogen bonding. So you're going to have hydrogen bonding between all the waters. And that is not a very strong bond, it's an intermolecular force, but because it's so much water and they're so close together, it's quite significant. Which one is the strongest of the inter forces, Harrison?
Inter?
Hombre, that's intra.
It's intra?
Yeah, there's inter and there is intra. Intra is ionic, covalent, and metallic, right? It's what puts
It's like
in.
hydrogen bond.
It's in between. So which one is the strongest of the inters? You know it? People have forgotten it in all the classes.
It's
Ion dipole.
Yes.
Yeah, so ion dipole is the strongest. The second strongest is what everybody's getting, which is hydrogen bond. The third one is what?
LDS.
Nope. Dipole, dipole. And the fourth one is LDS. Which, if you have a really large molecule, it can be quite significant and it can trump some of the others. If you have a really large molecule, because you have more electrons, more charges.
So what's the bond between the hydrogen and the oxygen?
Hydrogen bond. So what you have in here is you have a hydrogen. Let's put the hydrogen, I don't know, maybe red. And this hydrogen is in between two oxygens. No,
You just bonded
I
everyone.
bonded the wrong thing. I bonded two hydrogens together. That can happen. So this hydrogen, that hydrogen is in between two oxygens. It doesn't have to be oxygen. The hydrogen has to be in between two NOs or Fs in any combination. So if the hydrogen is in between those, you have a hydrogen bond. And in this case, we have two O's, so that's hydrogen bond. But that is all the inter forces that you have in there. Is all hydrogen bonding. We have a whole bunch of them.
Where did nitrogen come
What nitrogen?
from? And the fluorine.
Oh, what I'm saying is hydrogen bond happens when you have nitrogen, oxygen, or fluorine to the other, either one. In this case, we have two oxygens. It could have been two fluorines or two
And it's
nitrogens.
always a hydrogen bond.
Yeah, in between them. When the hydrogen is in between NO or F and NO or F, then it's hydrogen. If I had a carbon here, no hydrogen bonding.
But it can't go from oxygen to oxygen or nitrogen to nitrogen.
With the hydrogen in between.
Wait.
So the hydrogen has to be in between two oxygens or an N and an F or an O and an O or whatever. Any combination of NOF. Because this one is very electronegative, so it's gonna rub it, making this very positive. And this one is very electronegative, making this fairly negative. And that is gonna be fairly strong. Being electronegative, the oxygen will pull the electrons. This being electronegative is gonna pull the electrons. So that's very negative, that's very positive. That is a hydrogen bond. And it's very significant. Now here we have hydrogen bonding as well. But we also have something else. Between the OH and the water, what do you get? Hydrogen bonding. Anytime you have an OH, you will hydrogen bond to water, right? So this will also be hydrogen bonding. But what happens with the carbon? The carbon is, or this section, this is that section ionic, covalent, polar, what is it? What is it?
Covalent.
100% covalent, right? 100%, because carbon hydrogen is always, just like the atomic molecules, carbon hydrogen is always 100% covalent, always 100% covalent. So this is all carbon hydrogens. How can they bond to others? With London dispersion forces, very weak, right? Based on that, which one would you expect to have the lower boiling point, Bailey? Water or alcohol?
Is that what the C2H5OH is?
That's ethanol. C2H6 will be ethane. If one replace one H with an OH, is ethanol. So which one will start boiling faster? The water, according to you, the water or the ethanol? You said the ethanol? What do you think?
Sure.
Sure.
I don't know.
Tell me. Guess. I'm gonna ask the whole class.
Wait, why would it? What would make it boil faster?
The breaking of the bonds.
Breaking of.
You're gonna have to go into the vapor. You know, you're gonna have to, in order to evaporate, you have to go from a liquid to a vapor. You have to. Okay, what about you? What do you think?
The ethanol is. Wait. Hang on. I'm thinking water.
Amy, what do you think?
The lower boiling point, I think it's gonna be ethanol.
Water.
Anna Kate. Maeve. You. He's like, she's gonna skip me.
Water.
Excuse me?
Alcohol.
So, in order for you to boil, you have to be able to break apart the bonds and turn into that. This one has hydrogen bonds and hydrogen bonds that make them the same, right? But this one has these London dispersion forces for the carbon that gets in between the hydrogen bonding, which makes it weaker, right? It makes it weaker. So this one boils. When does water boil?
100 degrees Celsius.
And what about in degrees F?
212.
212 or 100 C. And this one boils at what? 178.
Fahrenheit?
Where are the London dispersion forces?
This can only bond to anything else through London dispersion. So this carbon chain is 100% covalent, and it could not do anything greater than London dispersion. So that is the carbon. What they say is the carbon gets in the way of the hydrogen bonding. So it is easier. So if I were to pour, which I did in the last class, I pour water, right? And if I were to pour alcohol, which one will evaporate quicker? The alcohol, right? And it actually smells immediately. As soon as I put it, it smells.
Is that why when you when you have a cut and then you pour it on it and then it's just like cold and then immediately goes away?
It becomes cold because the water is gonna go, the alcohol is gonna go from a liquid to a vapor. In order for alcohol to go from a liquid to a vapor, it has to absorb some energy, right? So it takes energy from you, making you feel cold, and it takes that energy to be able to become a vapor. It wants to become a vapor, and it grabs your energy and it turns into a
But it
vapor.
goes away so quick.
Yes.
Oh, that is disgusting.
Now, yes.
How do you spell ethanol?
With an A. Got it. 'Cause there's one, I didn't know if it was an A or a Y.
Ethyl alcohol is another name for ethanol. They can call it ethanol, or they can call it ethyl alcohol.
Okay.
I think those are the only two names for it. Ethanol or ethyl alcohol. Ethyl, because there's an ethyl group with an OH, and ethanol is just the whole thing. So however you want to call it, I normally call it ethanol, but yeah, a lot of people call it ethyl alcohol. It's potato. It's the same thing. Now, does this make sense? So, knowing this, the bracelet is in Amazon for $100. Somebody did break one.
Oh, that's
Do
so.
they have to buy it?
No, I don't know. Maybe I'll charge him.
How does that thing work?
But
Don't
What
put
is
it on
that
me, I'll
thing
break
full
it.
of red stuff?
so if you have,
Yeah, Miss Thompson, what's
What is that thing of red stuff?
we're gonna go to it in a minute. So if we have water,
Is this the same distillation though?
this is, yeah, the same thing. So if we have water and we have ethanol in here, and I want to separate them, the ethanol boils at 178 degrees F, the water boils at 212 degrees F. How would you separate them?
You boil it at a 178.
You have to be somewhere in between 178 and 212.
Like 190.
Usually they do it 180, but 190 will be fine, right? You want to be in between. You want to be higher than that, but not too close to that, because then you'll boil too much water, right? So when you do that, the ethanol, some of the water will also come because it's still attracted to the ethanol, but mostly the ethanol is going to come up with some water as a vapor, because we just broke the forces that kept it as a liquid. Some of the water is going to be bonded to this, and some water will come out with the ethanol. So you may have to distill it again if you want to make it more pure. But that's what distillation is to separate based on boiling points. You put it at a boiling point that is at a temperature that is in between. Usually they start closer to this one, and then you start boiling it up, and the ethanol mostly comes. Now over here we normally put something really cold. We put something really cold, like cold water, so that it grabs it and it makes it condense. and then we collect it. We collect it, and that's how they distill alcohol out of a fermentation of sugar cane, which is rum, or potatoes, which I think is whiskey.
What
And
is that blue box?
is you put something that is called a condenser. Basically, you have something that has, what you really do is you have a tube, you have water over here that is cold, and then you run your ethanol water gas through here, and by the time it comes out, it's a liquid. Because it cools it. When you cool off steam, it condenses and then it's able to drop in here as a liquid. And then you collect it. So that's called a condenser, because literally you just have cold water that is going to allow you to condense. Because nobody wants vapor alcohol, right? We want it as a liquid. Eventually it happens on its own. This makes it happen faster. So you have a condenser in order to get the alcohol. Those are the basics of distillation. Now, how are you gonna do it at home? Not like that. That is, you could do it if you want to, but you don't have to. What we're doing is something much, much simpler. You are gonna get a pot within a pot, or a Pyrex container within a pot. And you're gonna put your salty water or soy or whatever, anything. It could be soup, it could be seafood gumbo on the outside. Then you put a pot in the middle, or a Pyrex container, something to collect the water. And you're gonna boil this salt water solution. The salt will stay behind, right? So you're gonna be concentrating it, and the steam is going to come up. You don't wanna have it like 100 boiling, because you're putting too much energy and it may just boil up too much, and some of that may jump in here. We don't want anything jumping into the little pot. So it's about medium high. That's how you put it. This is your other pot. You put a little bit of water. Then you put the lid backwards, so that the steam as it comes up, because what will come up is literally just water, is going to come here. You put ice over here, so that, again, this is like your condenser. It's gonna get that steam, it's gonna condense it here, and it's gonna come and drip over here. And you're gonna collect a little tiny bit of 100% pure water without electrolytes. If you had alcohol, they'll boil with the alcohol as well, so you don't want that. But the salt will stay behind. The NaCl, you're gonna concentrate it, and if you boil up all the water, you'll end up with a film of sodium chloride in the bottom. Is that a bad thing? No. How would you get rid of that film? Just put water, dilute it, right? It has NaA, it's gonna dilute fairly easy. If you put sugar and you burn it, it's gonna be an issue to take it out. It bonds to the pot, and then you have to really scrape and nonsense. You can still dilute it, but it's gonna take longer. The sodium chloride will come off really quickly. You will not burn it. I don't care what you do, it won't be burned. So it's better to do it with sodium chloride. And that is showing how distillation happens.
What is the
just put the
definition of
burner.
distillation?
Distillation is separating a solution based on difference in boiling points. And the boiling points are normally close to each other. In this case, it's not, so this is not like the best
Does
example.
it
But
matter what we put the burner on, like high, medium, or low?
so I would rather you not put it too high, because sometimes when you put it too high, this boils like that, and some of that may actually jump in here. Some of that solution may actually jump if you put it too high. So you want it to be boiling, but not boiling too violently.
What does this route do?
When you come back.
Solution by using.
So when it's snowing outside, you'll be making salt solutions inside.
Wonderful. Lovely.
This takes a while. You don't have to do the whole thing. I just want you to at least put the stuff together, get a little bit and stop. You know, that way you will never forget what distillation is. If you don't do it, you will forget. Now, when do we use distillation? We live in Baton Rouge, the petrochemical industry. They have fossil fuels. They are a soup. The crude oil, the petroleum, is a soup of hydrocarbons. So you have different amounts of different chains of carbon, all with hydrogens. That's what you have. You have a soup of different, can have 8 carbons, 9 carbons, 10 carbons, 25 carbons, 26 carbons, right? You have this soup. They are all in the same solution, right? How do you separate them? You add heat, and as soon as it gets to a very low temperature, the first thing that is gonna come up is what? The things that have the lowest carbon chain, because the London dispersion forces are gonna be weaker, right? So this one, how does it bond to self? Very weak, not too many electrons, weak London dispersion. Those will come up first. In this case, we're having, hey, butane, it has 4 carbons, will come out first. If you increase the temperature, then this one will be at a higher temperature. You have your gasoline, which is somewhere between pentane and nonane, somewhere around there. It's a mixture. Gasoline is not just octane, it's a mixture. Then you have your naphtha, kerosene, diesel, those are harder and harder. Eventually, you have things like the bitumen that you put in the asphalt in your streets, that black tar that you put in there, that comes from these fossil fuels as well. You can get it to move like a liquid with enough heat, but it will solidify and it will not boil very quickly because we run our cars through it, right? So the boiling point of that is really, really high. I'm gonna miss those kids sometimes, you know? They come by all the time. There's also Reed, but he stopped coming. That's not him. So you have, oh, that's on the video.
Yeah, it's okay.
So you have things that are separated. Normally you don't have 4, 5, 6 different fractions. Normally you just have 2. Out of every distillation column, you have 2 things coming out, and then you have another one and another one and another one until you distill what you really want to get, right? That's what they normally have. And they look like this, but they're actually they're about this wide. They're not very big. You get better separation if you have a long, small column. If you make it too big, it's not gonna be the same. And this is very simple. We can look more into distillation if we finish early.
Can we take a 5-minute break
Let me see.
after this
please.
lab?
So after this lab, we'll do a break that I've been doing with the other classes. This thing is way too hot. What I did is I was teaching a camp and somebody gave me this mead or whatever. It's some liquor made out of lemon. I mean, not lemon, honeydew, but I didn't like it at all. You eat a little bit after your meal. And I told my son, why don't you create something so that we can take the alcohol out of that and distill it? So he grabbed a pickle jar and tubing and did something very rudimentary, not perfect, lots of room for improvement, but it worked. And he didn't boil it forever. It could have been dangerous. This jar is not for heat. It could have broken, right? We should have had other things in order, but it worked fine. So what he did is he made sure that the water, that the temperature in here was around the temperature where the alcohol starts coming up. And you had the alcohol and a little bit of water coming here. He had, again, a water bottle in order to help condense it. You don't want it to stay as a vapor, you help condense it. And then we collected a tiny, minuscule amount of ethanol with a little bit of water. How did we know that this was ethanol? He found the density. How would you find the density of that substance? How would you do that?
You did this at your house?
Yeah. So how would you find the density? You have the mass, you have a scale, which we do. Then you have the volume. You put this into a graduated cylinder, and you have your volume more accurately than that. And then we got the density, and we compared it to the density of ethanol, and the percent error, I forget, this was done a while back, was not too crazy. So we actually distilled the alcohol out of that drink. I used to bring it here and do it here, but it's illegal to bring alcohol to school.
Is
so
this
I
what we're
stopped.
doing at home when you do that?
No,
Or we just have to analyze that
You're gonna do the salty water.
Or like we have to tell you what your son did.
Oh, yeah, you have the video. This is the YouTube video. So you describe what happened, which I just told you what happened. And this is the video with the calculation.
We have to draw that because it's a sketch.
Yeah, you draw the distillation apparatus, right? And what?
What's the apparatus?
Basically that.
Just like draw.
Yeah, just draw what that is. Then there are some questions, and in here I grabbed some of the different intermolecular forces from weakest to strongest. We know them, we've seen them, but I just put them in there again. So you see what those intermolecular forces are. Oh. And okay, now if I want to increase, so this is the last thing before we do the, what should we do it now?
No.
Now? Okay,
Are you
so
gonna
what I'm
explain
telling
this?
people for the break, well, let's finish this just for the video.
Yeah, finish this lab.
So what this is saying is, if you want to increase the boiling point of something, you know, something goes from a liquid to a vapor when it gets enough energy to break apart, right? What if I am a water molecule and I not only have the pressure from the atmosphere that I have to overcome, but I have some things on top of me, like balls on top of me. So not only do you have the pressure from the atmosphere, but you have more pressure on you. That's gonna increase your boiling point, right? So if we put anything in the solution, it increases the boiling point, and that's showing how that happens. If you have a solution of something, this is called colligative properties, is going to increase the boiling point or decrease the freezing point. If you wanna freeze, you wanna make a crystal, but if there are things like ethanol in the way, they're not gonna let you make the perfect crystals, and you're gonna have to get way colder in order to freeze. So everybody's a little bit out to lunch by now.